Okay, I think we're live. So, hi everyone, welcome to another session. So, today we'll be solving two problems again, and today the topic will be trees. So, we'll be solving some easy questions on trees and then have a few questions for your homework as well. That's the agenda for the day. Now let's actually get started without wasting much time. Let's get started with the problem. Which one do we want to do first? Maybe this we can take up second. I think this is an easy problem, and this is a medium problem. Okay, so let's do one thing. Let's take this up first. First is if you have to tell whether a tree is a symmetric tree, right? So you are given a binary tree. Check whether it is symmetric or not. That is whether the binary tree is a mirror image of itself. So you have to tell whether it is symmetric or it is not symmetric, right? So that's the question. Now, when is it symmetric? So 5112, that's a symmetric tree, but the next one is not a symmetric tree. So let's first understand when is a tree symmetric, and the complexity will be order of n time and order of height of tree as the space complexity. Okay, so let's understand first what is like how do we identify a symmetric tree. So let's say we have a tree something like this, that one, let's try to draw a good symmetric tree. So two, and we'll make this symmetric. So two, let's say here we have three, four. So how will the mirror image look like? It will be something like this. uh, if we take the mirror image for this, how will it look? It will look like this: one, two, two, four, three, something. So this will not remain a symmetric tree, right? Because when we take the mirror image, it will become 4 3, although like we can have 4 3 here. Does that make it symmetric? Let's see. So it will be 4 and then 3. Yeah, I think this will remain symmetric. 3 4. uh they're reversed, everything is reversed. Okay, 4 3 and 3 4. And after that, let's say we have some other nodes, but again, like we can have multiple. So this is a symmetric tree, right? If we bring a mirror in between them, see that it still remains the same. So this tree is a symmetric tree. So we have to determine if a tree is symmetric or it is not symmetric. Now how do we prove what is the condition for a tree? We see that the condition for a tree to be symmetric is if like if we interchange the, so this will basically like, what we can do is, instead of like finding if the tree itself is symmetric, we can see if two trees are symmetry of itself or not. So what we can do is we can generate this, we can compare this tree, the second tree, with the first tree and see if they are equal or not. If they are equal, then the tree is symmetric. Like we'll take the mirror image tree, we'll take the mirror image tree, this is the mirror image. We'll compare the actual tree with the mirror image and we'll see if they are equal or not. And if they are equal, in that case, we'll tell that they are symmetric, right? So how do we actually take the mirror image? So in mirror image, see what exactly is happening. The left and the right childs are getting swapped. Nothing else, right? The left child is becoming the right child. The right child is becoming the left child. So that's a mirror image, right? So what we can do is, the first way will be, we'll construct this tree by swapping the left and the right child for the first tree. So how will it look like? 1, then swapping 2 and 2, it remains same, 2 2. Then swapping the left and the right child, again left and the right child here as well. So here this 2 and 2 has been swapped, so 2 is coming here. So this left and right child will be swapped, so it will be 4 3. And this left and right child will be swapped for this, so it will be 3. And like that it will continue. So we can generate these two trees and then we can check them one by one, like starting from the root. If it is equal, okay, we'll continue our DFS or a search on the subtree. So we'll go to the left subtree, we'll see if the subtree is equal. So 2 and 2 are equal, so we'll continue our search. 4 4, 4 and 4 are equal, so that's done. So we'll come back to 2 again. So next we'll come back to 3. 3 and 3 are equal, so we'll come back to 2, so this entire subtree is equal, so we'll come back to 1. Now we'll go to 3, and like that we'll continue, right? So sorry, this would, so like this will continue, and we'll see that they are equal, so they will be mirror tree. Now this would need a order of n time complexity and order of n space complexity as well, because we are generating the tree again, the mirror tree again, right? What we can do, a better way can be, let's say we write a DFS and bool DFS that actually tells whether two trees are equal or not, right? So it will take node star root 1, node star root 2, right? Now exactly what happens in a mirror image, our the two child nodes get interchanged. So can't, instead of like making creating the root 2 again, what we can do is we can just call DFS for the actual root comma root, right? And how we'll do the DFS here is DFS root 1 of left, that will be compared with root 2's right child. Root 1's left child will be compared with root 2's right child, because in mirror image the right child will become the left child, so that's why we are comparing with the right child. Similarly, DFS root 1's right child will be compared with root 2's left child. Again the same reason, because in mirror image the left and the right child are getting swapped, right? Left and the right child are getting swapped, so that's why what we'll do is, instead of creating a new tree, we'll use the same tree for comparison, but when we recurse, we'll recurse for the left child in one tree and the right child in the other tree, because in the mirror image the right child will become the left child, so that's why we'll do that, right? Similarly, we'll recurse for right child in one tree and the left child in the other tree. So that should be that will be the code for this, and this will prove, like this will say whether two trees are symmetrical or not. Let me know if you have any doubts, otherwise we can go to the code for this. Let me know if you have any doubts with this. So let's go to the code for this. Is symmetry, right? So this will tell whether a tree is symmetrical or not. So if root of root equals to so let's make a private method, bool underscore DFS struct, or let's call it is symmetrical. Bool is symmetric. Let me know if you have any doubts, and struct node star root 2. Now if root 1 equals to null and root 2 equals to, if both of them are null, will return true. Else if one of them is null, so if root 1 equals to null or root 2 equals to null, if one of them is null, then we'll return false. So if else if root 1 of data is not equals to root 2 of data, in that case return false. Else return root 1 of data is equals to root 2. It is already equal as we are coming here. And second thing is symmetric. The left subtree of it with the right subtree of it, so root 2 of right, and also is symmetric. Root 1 of right, root 2 of left. So return underscore is symmetric root comma root. We'll start from the root node for symmetry, and we'll continue like this. Let's run this. It's coming true, what that is expected, so let's submit. Okay, so this is working, right? So this is how we can check if two trees are symmetrical or not symmetrical. Pretty simple. I hope that you don't have any doubts. Let me know if you have any. Next, we'll come to the question. This is a bit tricky one. So what we have to do is we have to find the lowest common ancestor in a binary tree, right? So we have to find the lowest common ancestor in a binary tree. Now, as the tree is binary, I'm not sure if you know about this, but again, like many of you might already know about this, that to find the lowest common ancestor, we use something called binary lifting to find the lowest common ancestor. So but when it comes to a binary tree, uh, we do not actually need that binary lifting to compute for binary tree, although we can use binary lifting as well to compute for a binary tree, but we generally do not need that. So when it comes to your interview question that you have to find the lowest common ancestor for a binary tree or a binary search tree, then um you don't have to use binary lifting, rather you can just use normal things and calculate it, right? So let's solve the harder version of the problem. So the easier version would be solving it for a bst. For binary search tree, it will become much easier because the data is arranged in certain way, so you can make a decision if the current node is lca or not. But for a binary tree it's a bit tricky, so we'll solve that. So we are given a binary tree with all unique values and two values n1 and n2. The task is to find the lowest common ancestor of the two given nodes. So we are to assume that both n1 and n2 are present in the tree and none of them are present, or none of them are present. So our task is to find what is the lowest common ancestor for the two given nodes, right? So lowest common ancestor, what is the lowest common ancestor definition? It is, if we move from two nodes towards the root node, the first ancestor which is common to both of them is the lowest common ancestor. So let's say we have two nodes and there is a path to the root node. So the first node, if we walk upwards towards the root node, the first node that is common for both of them will be the lowest common ancestor. So for example, 1 2 3, for 2 and 3 the lowest common ancestor will be 1. For 3 and 4, what is the first node that is common to both of them in their path towards root? It will be 2. So the 2 will be ancestor. Now you might think about this, that hey, what we can do is we can start from the both the nodes and we can move one step at a time, right? So you can think like this, that we start from both the nodes and we move one step at a time, but that will not work, right? That will not work. Why? I'll give you a reason. Let's go to the whiteboard. Let's say you have 1 2 4 5 7. Let's say you want to find the LCA for 4 and 6. What will be the LCA? The first node towards the root that is common for both of them. So 2 will be the LCA. So if you move one step at a time, for 6 you will move to 5, and for 4 you will move to 2. In the next iteration, for 5 you will move to 2, and for 4 you will move to 1. So you have actually crossed the LCA, right? The LCA was 2, so you are actually crossing the LCA. So moving one step at a time from both the nodes towards the parent node will not work. So how do we do this? And also we will not use binary lifting as well. So how do we do this? So we will use simple DFS only. Let's write it down like 4 5. So we start from the root node. Now for a given node, if both if both the child nodes are at so for a given node, if both the child nodes are on the same direction, then that is a possible LCA, right? So for example, let's say we are searching for 4 and 5, like let's mark these two nodes. We are searching for 4 and 6. Sorry. So for the first node, both the child nodes are on the same direction, on the same side. So this can be a candidate LCA. We'll go to the left subtree. So for 2, both 4 and 5 are working on the, or 4 and 6 are working on the right, left, are not working on the same subtree. They're not working on the same subtree. So this is the first place where they are bifurcated into different subtree. So this is a possible value of LCA, and these are not possible values for LCA, right? So we have to find what is okay. So that's the question, and that's what we have to find, which one is the LCA. So what is the first node where it is bifurcated into parts? That will be the LCA, right? So how do we do this? Let's understand that. Okay, so what we'll do is we'll maintain two things. That is the when we do a DFS, right? When we do a DFS, we will check if both values are in the subtree. If both values are in the subtree, that case this can be a candidate LCA. Otherwise, it will not be a candidate LCA. For example, for the root node, both the nodes are in the subtree. Both the child nodes are in the subtree. So this is a candidate LCA. For 2, both the child nodes are in the candidate subtree, so this is also a possible LCA. For 4 it is not, for 5 it is not, for 3 it is not, right? So we'll return back the control to 2 and we'll print 2 as the answer, because that is the last node which has from in the DFS, that is the that will contain the information if both the values are present, right? So how do we implement the DFS now, right? How do we implement the DFS now? That will be a bit tricky. So DFS, let's say we pass in the root node here. What we'll check is if root of if DFS of left. So we'll do DFS root of left, we'll do DFS root of right, right? Then what we'll do, we'll check if, so we'll maintain two variables, if the left subtree contains, or if the right subtree, if the first element is contained, or if the second element is contained. So if first element and then second element, right? So we have found both the elements. In that case, return what we will return true, that this is a the possible this is a possible this is a possible LCA. Otherwise else, return false. Okay, else return false. So also we'll add a condition check here, that if first L and second L, that's true, and if both of them are true, I think that's already taken care of here. So first element and second element is both of them are present in the same subtree, then return true. Otherwise, return false. That's true. That's true. And also we have to check. So we'll get the answer one here, or we'll get first element and second from the DF. Get that as well. Also one more thing can be here. That should be. So let's actually verify for this tree I have here. Let's verify for this tree. 5. Let's start the DFS. And also we'll maintain two variables is left. So we'll start from here. Now we'll go to the next one. Come here. From here we'll come to 7. Now for 7 we do not have a left child or a right child, and we are finding the LCA for 4 and 6, right? So is 7 equals to any of 4 and 6? No, right? So this will return false. This will also return false. So this side become false. And we'll come to this side. 3 and 4. Sorry, 3. Okay, for 3 it is not equal, so we'll call for 4 and 6. For 4 and 6, 4 and 6, sorry, 4 and 5, uh, 4, the value is 4 is true, but 5 it is not true. So first of all we'll come to 4 and we'll mark is left as true. Is right is not given yet, so we'll come here, we'll come to this. So 5, for 5 we do not know yet, so we'll move to 6. For 6 it is one of the values, so for 6 is right is true. So now this way we become we get both 3 and 2, we get both 3 and 2, like we get that 3 is the LCA for 4 and 6, right? So we set the is left and the is right, and then we determine which one is the LCA, right? Because for LCA both the nodes should be on the same side, either on the left or on the right. So it will, both the nodes will be in the subtree. So node n1 n2, so let's maintain a few variables. Node star answer and bool is left found, or is n1 found, bool is n2 found. So bool DFS node star root, node star root, and n1 and n2 we want to find the LCA. So, and first thing here is n1 found equals to false, is n2 found is equals to false initially. So in DFS we'll check if root equals to run null, return false, or return, let's have a void DFS, return, else if root of data equals to n1, root of data equals to n1, in that case is left found equals to true. If root of data equals to null, if root of data equals to n2, in that case is right found equals to true. Finally what we'll do, if it is not both of them, so what we'll do is bool or DFS root of left, dfs root of right. If answer not equals to null and is left found and is right found, answer equals to root. Is n1 found false, is n2 found false, and is n1 found. Is n1 found and is n2 found. And dfs root n1 return answer, right? So return answer, try to run. It's not working. dfs root left n1 and so this is run. We still are. Is left found is not declared, so it will be is n1 found. N2 found. So it's coming properly. Let's try to submit. Okay, 7 1 10 2 9 1 10 7 1 10 null 2 9 11. We have to find for we have to find for 9 and 10. 9 11 10. The 7 is the number of 7 is the number of 7 10 9 10. We have to find the LCA for 9 and 10. 9 and 10. Then 110 null, 110 and null, 2 and 9. Okay, so so we haven't taken care of the case that if one of if it's a parent node, right? If you are finding the LCA for a parent node, let's see if that actually comes under this. I believe it's not coming under this, but let's see. So 1 1 10 n 10 null 2 9 10 null 2 9 11 n 2 9 11 10. Oh, sorry, 11 n 4 8. 11 n 11 here, I think 4 8 something. We are finding for 9 and 10. So what will happen? First of all, DFS will start here. From here it will go to the left child. For left child, it will see if it is equals to n1, that's 2. Oh, okay. So we are setting it before only, right? We are setting it before only. Rather, what we should do is, first of all, we should DFS for the child nodes and then set this, right? Otherwise, think what happens here. For this, the right child is this. So here, just think about what happens, right? Here, if we set, we are setting. If you remember the code, we are setting. Is n1 found, is n2 found before dfsing, right? Now see what happens here. Here n2 is found, right? So is n2 found is set to true. Now we go to 2, we don't find anything. We go to 9, we find n1. Is n1 found is set to true, right? So that's why we here both of them, both the conditions are satisfied, and this is returned, or this is referred to as the lca, right? So I think, sorry, yeah, I think that's why it is referred to as the lca. So what we need to do here is 7110. What we can do here is, instead of this, we will be marking this after this, and then it should work. So let's actually try out this input now. 910. uh, our output is still 7. Okay, how is the tree constructed? The first line should contain 20 elements. The second line contains a string s denoting the binary. Okay, denotes the binary tree. So 7 is the root node here. So let's it denotes the binary tree. So 7 becomes the root node here. The tree was wrong that I've drawn. 7 1 10. Let's clear everything. 7 1 10. 7 1 10. N 2 9. N 2 9. N 2 9 11 N 4. 11 N 4. So for this, we want to find for 9 and 10. For 9 and 10, it should be 10 and not 7. So let's see how we get 10. So we'll start from here. We'll DFS to left and right. So for left subtree, we do not find anything. Let's come directly to the right subtree. So for right subtree, here we do not set anything. First of all, left and right is called. For left, we find n1. So is n1 found? Is n1 found is set to, then we come back here, and then we go here, we do not find anything, come back here. Now here we set is n2 found as well. Is n2 found equals to, now here basically we have found both of them, right? In this subtree we have found both of them. Okay, one more thing, change subtrees. When we change subtrees, that's also something that we have to consider. One found is on the left, and n2 might be on the right. So in that case, that might be a bit tricky. Okay, so in this case it will be a bit tricky. Let's say n1 is on the left, n2 is on the right. In that case it will be a bit tricky. Why it will be? Because just think, 9 is here somewhere, and 10 is here. So here will mark is n1 found to be true, here will mark is n2 found to be true, and this should have been the lca, but this will be referred to as the lc, right? So that's why it will be a bit tricky. So what we can do here is, when we are dfsing into a subtree, we'll reset all the values. When we are dfsing in the subtree, we'll reset all the values. When we are coming out of that subtree, we'll set all the values again, right? We'll set the proper values again. So uh, that's something that we can do. That's something that we can do, yes. Or what we can do is, for every node we return a pair if we have found n1 in that subtree, or if we have found n2 in that subtree, and the first node to have both of them to be set to true, that will be that, that will like be the answer, right? So let's, instead of void dfs, let's do a pair bool bool dfs, is n1 is n2. Let's get rid of that. So root equals to null, root equals to null will return false false. Else if so firstly dfs will call pair bool bool answer equals to dfs pair bool bool left answer dfs root of left n1 n2. Now if left answer is root of left n1 n2, and if root of data equals to n1, l answer also, let's take the right answer as well. So pair bool bool our answer equals to dfs root of right n2 n1 n2 is found, everything is set. So answer equals to initially null. So we have dfs for left and the right subtree. Full screen into Chrome. Sorry. Go full screen. Here is, I think, here. So, okay. For left answer and right answer, we are DFSing. So this returns whether in the subtree for root of left, if we have both n1 as well as n2. For right answer, we in the subtree of the right child, if we have both n1 and n2, that is contained by this pair. Now, if current node, if root of data is equals to n1, in that case l answer dot first equals to true, r answer dot first equals to true. Else if root of data equals to n2, in that case l answer dot second equals to true, r answer dot second equals to true, equals to true. Now if answer equals to null, now if l answer dot first and r answer dot first, sorry, l answer dot first and l answer dot second, if everything is present in the left subtree, if r answer dot first and r answer dot second, if everything is present in the right subtree, both the n1 n2 are present in the right subtree, in that case answer equals to root. Here also answer equals to root. So we could have just done a odd operation, but let's keep that separate and return what will be returned. What will be returned is basically l answer dot first or r answer dot first. If one of them is true, then it should be true. R answer dot first comma l answer dot second or r answer dot second. So if one of them is true, the other one has to be true. If one of them is true, then in the subtree it is present, so we'll return like this. That this is what will return. So answer and root n1 n2. So compile and run. And what should we return if it is not present? Is anything given? Is given. So we are running into a segmentation fault. Let's see. So if root of equals to null, then return false. Otherwise we are calling root of left n1 n2 and root of right n1 n2. Now root of data equals to n1, first and r answer of first equals to true. Root of data equals to n2, then l answer of second and r answer of second equals to true. So answer equals to null if answer is null, if l answer dot first and r answer dot second answer equals to l answer dot second answer equals to root, r answer dot first and r answer dot second answer equals to root. If it is both in the left subtree or if it is in the right subtree completely, then answer equals to root if it is present in the subtree. Basically, if it is present in the subtree, right? So if bool is n1 present, is n1 present, so that is L answer dot first or R answer dot first. Bool is n2 present equals to L answer dot second or R answer dot second, and will return this is n1 present, is n2 present, is n1 present, is n2 present. If answer equals to null and is n1 present and is n2 present, answer equals to root. Both n1 and n2 are present, and this is for the first time they are present, so it will be at the lowest node, right? So answer equals to null dfs root n1 n2 and return answer. So pair L answer, let's see if this works. So we are returning false false and compile and run. Let's do compile and run. It's coming as expected. Let's try to submit. I believe my net is low. Okay, so this is also done. So what we have done is we have calculated for every node if n1 is present within the subtree, if n2 is present within the subtree. Now if both n1 and n2 are present within the subtree, this can be a LCA. For that, what do we want? We want the lowest node, right? So when we DFS, the first time we visit a node for which both of them are set, it will be a lower node, right? Because in DFS first we go deeper and then we check, then we come up, like after, like we are going deeper using this DFS and then we are running these commands, right? So it will be the first node at the maximum depth which has both of them present, which is the LCA. So that's why if answer is null, then we are setting the answer to root provided both of n1 and n2 are present, right? So this is how we can solve this problem, like how to find the DFS, how to find the LCA of a binary tree. The complexity for this will be order of n time complexity because we are just doing a DFS, and the space complexity will be the DFS complexity, that is height of the tree, right? So these are the two questions for the day. Now for your homework you have these problems. So first is check if subtree. In this you are given two binary trees and you have to check if the second binary tree is a subtree of the first binary tree. Second is a easy medium problem, it's diagonal traversal of a binary tree, so it's more like a traversal of a binary tree. So solve this as well. And the third one is a easy problem, which is lowest common ancestor of a BST. Now for a binary tree, the problem was that it's not a balanced search tree, so we had to do a lot of things. But for a balanced search tree, we have a very important criteria condition, that is all the nodes on the left hand side will be smaller, all the nodes on the right hand side will be greater than the current node. So we can leverage this to find which way to go when we are finding the LCA, right? Because let's say n1 and n2 both are less than the current value, so the LCA will also be on the left hand side. If both of them are greater value, so the LCA will be on the right hand side. If one is lesser, one is greater, so this will be the LCA, something like that, right? So that's how we can leverage that and find the LCA. So these three will be the homework: lowest common ancestor in a binary search tree, diagonal traversal of a binary tree, and check if subtree, that is if a tree is subtree of another tree. So these three are the questions, and today we have solved symmetric tree, if two trees are symmetric, and lowest common ancestor in a binary tree. So let me know if you have any doubts. I'll wait for maybe 1 minute and then we can end. So let me know if you have any doubts with this one, lowest. Any doubts with lowest common ancestor? Okay, I don't think you have any doubts. So in that case, like if you have doubts, just rewatch the video. I believe this should be clear, like how we have done this. So basically, we are just finding when we are DFSing, we are finding if both the nodes are present within the subtree or not present within the subtree, and then we are using leveraging that to find the lowest common ancestor. So, yep, thank you guys for joining in, and I'll be seeing you guys in the next class. That is, the next class will be on Monday and Sunday. Let's see if I will be taking the interviews. So, thank you guys for